Ladies and gentlemen, let me begin with a simple but powerful question. Why do so many people over 60 begin to avoid social interactions, even those with family or old friends? We often assume it's just about physical decline, grumpiness, or generational gaps. But neuroscience and psychology tell a very different and frankly shocking story. The truth is, the brain doesn't just age biologically, it adapts based on perceived safety, relevance, and reward. And in later decades, these three filters begin to shift dramatically. Many older adults start to feel unseen, unheard, or even irrelevant. This isn't just emotional, it's neurological. As the dopamine system naturally downshifts with age, the motivation to seek novelty or connection reduces. Couple this with loss, grief, and sometimes a shrinking sense of purpose, and the brain rewires to prefer solitude. But here's the paradox. The very isolation they lean into accelerates cognitive decline, emotional instability, and even physical aging. Avoidance becomes a form of self-protection, but it ends up hurting more than it helps. But here's the empowering part. This isn't irreversible. Our brains remain plastic even past 60. With the right inputs, social, emotional, cognitive, we can reshape those circuits and re-engage meaningfully with life. So today, let's uncover the science behind this behavior and, even more importantly, what we can do to change it. As we age, one of the most significant yet under-discussed changes in the brain involves the dopamine system. Dopamine is a key neuromodulator responsible for driving motivation, reward anticipation, and goal-directed behavior. It plays a central role not just in initiating action, but also in sustaining the effort required for social engagement. After the age of 60, there is a natural decline in both dopamine production and receptor sensitivity, particularly in brain regions like the ventral tegmental area, VTA, and the nucleus accumbens. These areas are crucial for evaluating the emotional and motivational value of social interaction. This decline doesn't just affect enthusiasm for new projects or physical activities, it directly reduces the perceived value of social connection. The effort it takes to initiate or maintain a conversation, attend a gathering, or even make a phone call begins to outweigh the anticipated reward. Importantly, this isn't a conscious decision to withdraw from others. It's a recalibration of the brain's cost-benefit analysis. The energy cost feels high, the dopamine reward feels low, so avoidance becomes the default. Moreover, because dopamine is tightly coupled with novelty-seeking behavior, older adults may lose interest in meeting new people or engaging in unfamiliar environments. Instead of feeling invigorated by the idea of a spontaneous visit or a lively discussion, they may feel overwhelmed or indifferent. This creates a self-reinforcing loop. Less engagement leads to less stimulation, which further downregulates dopamine signaling, and that in turn deepens the social withdrawal. The critical insight here is that this shift is biological, not purely psychological. It's not about becoming antisocial or set in one's ways. It's about a neurochemical system no longer pushing toward the same social rewards it once did. Understanding this helps eliminate blame or misunderstanding and opens the door to targeted interventions that can reintroduce stimulation and meaningful connection in biologically supportive ways. As we age, the brain begins to shift its preference from novelty and exploration to familiarity and routine. This isn't just a psychological tendency, it's a neurobiological adaptation. In younger individuals, especially those under 30, the brain is highly tuned to seek out new experiences. Novelty activates circuits in the hippocampus and prefrontal cortex, boosting dopamine release and enhancing learning, memory formation, and social bonding. But after midlife, particularly post-60, the neural response to novelty begins to attenuate. What happens instead is a recalibration of the brain's reward system. Familiar environments, faces, routines, and even predictable conversations start to feel safer and more neurologically efficient. This is partly due to reduced neuroplasticity. Fewer new connections are formed, and the brain leans more heavily on well-worn pathways that require less metabolic energy. There's also a shift in activity from the ventral to the dorsal striatum, areas more involved in habit formation and routine-driven behavior than in seeking out the new or unexpected. This shift is compounded by changes in the amygdala and anterior cingulate cortex, regions involved in emotional processing and error detection. In an older brain, novel stimuli are more likely to be flagged as uncertain or even threatening rather than exciting. That means new social settings, unfamiliar people, or conversations outside one's regular topics may generate a mild stress response, subtle but enough to create avoidance over time. Over the years, this bias toward the familiar can narrow the scope of social engagement. People begin to socialize only with those who share long histories, similar viewpoints, or highly predictable behavior. While this feels comfortable, it also reduces exposure to cognitive diversity and emotional novelty, two key ingredients in maintaining brain vitality. The danger isn't just psychological isolation, it's neurobiological stagnation. Familiarity may feel good in the moment, but in excess, it dulls the circuits that keep the brain adaptive and engaged. Reintroducing low-stakes novelty, such as brief, new conversations or unfamiliar environments paired with safe context, can gently reawaken these neural systems. The goal isn't to push the aging brain into constant change, but to preserve its flexibility by keeping the circuits for novelty and curiosity subtly engaged. As people move into their 60s and beyond, one of the most underestimated yet deeply impactful changes occurs in the sensory systems, particularly hearing and vision. While these might seem like simple mechanical deficits, they have profound downstream effects on social behavior, emotional interpretation, and even cognitive function. Take hearing, for example. As auditory acuity diminishes, especially in noisy or multi-speaker environments, the brain has to work significantly harder to parse out speech, tone, and emotional cues. This increased cognitive load doesn't just make conversations tiring, it changes how they're experienced. What was once a fluid back-and-forth exchange can start to feel fragmented, effortful, or even anxiety-inducing. The individual may begin to misinterpret what is being said, feel like they're missing context, or worry they're responding inappropriately. That subtle erosion of confidence becomes a powerful deterrent to engaging in future conversations. From a neurological standpoint, this makes perfect sense. When the auditory system is compromised, the brain receives incomplete or distorted inputs. The superior temporal gyrus, responsible for decoding speech, and its connections with the prefrontal cortex and limbic system, are forced to fill in the gaps. But these compensations come at a cost. The increased demand on attention, working memory, and emotional self-monitoring can leave a person mentally fatigued after even brief social contact. Over time, the brain learns to associate social interaction not with reward and connection, but with strain and ambiguity. That's a major shift. Vision loss has similar effects, though it often operates more subtly. Nonverbal communication, facial expressions, eye contact, microgestures, forms a critical portion of how humans regulate conversations and interpret emotional tone. When visual acuity declines, those signals become muffled or missed entirely. This can lead to miscommunication, social friction, or the mistaken belief that others are being cold, dismissive, or hostile. In reality, it's simply a failure in the feedback loop. The brain is no longer receiving enough accurate input to make confident interpretations. And when the sensory data is unreliable, the brain begins to disengage as a protective mechanism. Crucially, this isn't about personality change or intentional withdrawal. It's a neurobiological adaptation to degraded input. The social brain relies on a rich stream of sensory information to calibrate responses, detect empathy, assess safety, and mirror emotions. When that stream becomes patchy, the brain reduces output to match the declining quality of input. This is why many older adults report that conversations feel flat or draining. The emotional resonance is diminished because the sensory circuits that support it are impaired. The encouraging part is that the brain remains plastic. Even in later years, supporting sensory health through hearing aids, lighting adjustments, environmental modifications can reopen those social feedback loops. Once clear, consistent input is restored, the brain begins to re-engage. Social interactions become rewarding again, not because of a shift in personality, but because the neurological friction has been reduced. This is why early intervention in sensory decline is not just about quality of life, it's about preserving the biological systems that make social connection possible. As we get older, certain neural systems begin to shift in subtle but profound ways. And one of the most critical changes involves the brain's fear and threat detection networks. In particular, the amygdala, a key region for processing fear, emotional salience, and social evaluation, shows altered patterns of activation in later life. Contrary to what many assume, it doesn't always become less responsive. In fact, in many individuals, it becomes more sensitive to perceived social threats, especially those involving rejection, irrelevance, or unfamiliarity. This heightened sensitivity isn't about being paranoid or pessimistic. It's the result of decades of accumulated experience interacting with a brain that's trying to conserve resources. As the brain's dopamine and serotonin systems gradually decline, emotional regulation becomes less efficient. The circuits responsible for down-regulating fear, primarily in the prefrontal cortex, start to lose their grip. These top-down control mechanisms, which once helped dampen social anxiety or recalibrate emotional misinterpretations, begin to weaken. As a result, the brain becomes more reactive to subtle cues that might signal exclusion, confusion, or criticism, even if those cues are misread. At the same time, the anterior cingulate cortex, which plays a role in monitoring social errors and conflict, remains active and, in some cases, overengaged. This means older adults can become more preoccupied with what others are thinking, whether they're being understood, or whether they've said something wrong. It's not always overt, but neurologically, the vigilance system is quietly ramping up. This creates a kind of background noise in the brain, a sense of uncertainty or potential judgment that makes social interactions feel more emotionally costly. It's important to understand that this doesn't happen in isolation. When you combine this increased amygdala sensitivity with slower information processing, reduced working memory, and declining auditory or visual clarity, the brain is left in a position where it has to work much harder just to keep up with a conversation. That increased cognitive effort, layered on top of the heightened emotional reactivity, can trigger a feedback loop where the brain starts to associate social environments with unpredictability or even mild threat. What results is not a conscious desire to withdraw, but rather a learned automatic avoidance behavior. The brain subtly begins steering the individual away from the types of interactions that challenge its emotional stability or cognitive capacity. It seeks safer ground, solitude, routine, quiet, where the threat detection system can relax. From a neural standpoint, this is a form of protection. But over time, that protection becomes a prison. The very circuits that evolved to keep us safe from danger are now keeping us distance from connection. Yet, this pattern is not fixed. Neuroplasticity remains alive in the aging brain. Exposure to positive, low-stress social environments, especially those with clear structure, empathetic communication, and low sensory load, can begin to rewire these patterns. Even short interactions that are predictable and emotionally safe can start to dial down amygdala reactivity. Over time, this recalibration can restore confidence, reduce baseline anxiety, and reintroduce a sense of reward to social engagement. So, while it's true that the fear processing centers may become more active with age, that doesn't mean they have to dominate. Through intentional behavior, supportive environments, and awareness of these hidden brain mechanisms, we can help older adults move from avoidance to connection without forcing it, but by engaging the nervous system on its own terms. One of the most overlooked drivers of social withdrawal in people over 60 is the gradual loss of purpose, and the neurological consequences of that loss are deeper than most people realize. From a brain function standpoint, purpose isn't just a philosophical or emotional construct, it's a neural imperative. When someone has a clearly defined role, whether it's professional, familial, or community-based, the brain organizes its activity around goal-directed behavior. That process heavily recruits the prefrontal cortex, the brain region responsible for planning, decision-making, attention, and social cognition. This area, the prefrontal cortex, is metabolically demanding. It doesn't simply activate passively, it thrives on challenges, structure, and a future orientation. When a person retires, experiences an empty nest, or loses a major social or caregiving role, the daily demands on that system can drop precipitously. Over time, without consistent engagement in goal-relevant behavior, the circuits that support executive function start to downregulate. The result isn't just cognitive arrest, it's a measurable reduction in neural activity in regions that are essential for interpreting complex social cues, regulating behavior, and maintaining motivation to engage with others. When someone no longer feels needed, when they don't have something to prepare for, contribute to, or be accountable within, the brain receives less frequent reinforcement to maintain high-functioning cognitive maps. This is a form of neural, unuse it or lose it. The dorsolateral prefrontal cortex in particular, which plays a key role in working memory and perspective taking, becomes understimulated. And that understimulation carries consequences: diminished social curiosity, slower reaction times in conversation, and a lower tolerance for ambiguity or disagreement, all of which can make social interaction feel less rewarding and more effortful. But the effects go beyond cognition. They also involve identity. Our sense of self is encoded not just in memory, but in ongoing narrative processing. The brain constructs a cohesive sense of who we are by integrating past experiences with future intentions. When future-facing goals begin to disappear, that narrative coherence starts to erode. People often say they don't feel like themselves after retirement or after losing a central role, and that's not metaphorical. From a neurological standpoint, the absence of purpose leads to fragmentation in how the medial prefrontal cortex encodes self-relevance. When that circuitry begins to quiet down, motivation and emotional regulation tend to follow. This also affects the brain's reward system. When we work toward goals or contribute meaningfully to others, the brain releases a combination of dopamine and serotonin. These not only reinforce behavior, but also modulate mood and resilience. In the absence of that purpose-driven reinforcement, reward pathways become less active, and over time, the threshold for feeling pleasure or satisfaction can increase. What once felt fulfilling, conversation, teamwork, teaching, mentoring, can begin to feel flat or distant. And this is where social withdrawal often begins, not from disinterest, but from a reduced capacity to a derived interest. The brain is no longer being cued to see people and events as relevant to personal goals because the goals themselves have vanished. Social interactions without context or purpose feel like static. The motivational circuitry doesn't light up, the prefrontal cortex doesn't engage, and over time, the person may begin to retreat, not just from others, but from their own forward-facing identity. The good news is that this process can be interrupted. Purpose isn't something that has to come from career or family legacy. It can be rebuilt through micro-goals, contribution to others, skill learning, or mentorship. Even something as simple as being responsible for a garden, a pet, or a volunteer task can re-engage those prefrontal circuits. With consistency, the brain begins to recalibrate, task relevance increases, attention stabilizes, and social interactions become infused again with meaning. Purpose, in that sense, is less about productivity and more about neural activation. And for the aging brain, few things are more protective. When we think about loneliness, we usually frame it as an emotional state, something that resides in the mind, shaped by circumstance or mood. But in recent years, a growing body of research has made it unmistakably clear: loneliness is not just a feeling. It's a physiological condition with deep and measurable effects on the brain and body, particularly through the pathway of neuroinflammation. Here's how it works. The human brain is fundamentally a social organ. Evolution has wired it to depend on social bonds for survival, regulation, and signaling safety. In fact, the absence of meaningful connection is interpreted by the brain as a form of threat. That perception triggers the activation of the hypothalamic pituitary adrenal HPA axis, the body's primary stress response system. Once activated, the HPA axis floods the body with cortisol and other glucocorticoids, preparing the system for short-term adaptation. But when loneliness is chronic, that system doesn't turn off. Instead, it remains in a low-grade activated state, leading to persistent elevations in stress hormones. Cortisol itself isn't inherently damaging. In acute doses, it helps us respond to challenge. But over time, elevated cortisol levels disrupt the blood-brain barrier, allowing peripheral immune molecules to cross into the brain. This sets the stage for increased release of pro-inflammatory cytokines, molecules like interleukin-6 IL-6, tumor necrosis factor alpha TNF-A, and C-reactive protein CRP. These are not just markers of inflammation, they're active agents in reshaping neural environments. Once these cytokines reach the brain, they begin to alter synaptic function. Microglia, the brain's resident immune cells, shift into an activated state, pruning connections, reducing neuroplasticity, and dampening neurogenesis. The hippocampus, critical for learning and memory, is especially vulnerable. Its sensitivity to inflammatory signals means that persistent loneliness can impair memory formation and increase the risk of neurodegenerative processes. In fact, longitudinal studies show that older adults who report high levels of loneliness exhibit greater hippocampal atrophy and reduced gray matter volume over time. And it doesn't stop there. Inflammation disrupts the function of the prefrontal cortex, the region responsible for executive function, impulse control, and emotional regulation. This disruption impairs decision-making and increases reactivity, which can further degrade social interactions. When someone is lonely, their brain becomes biologically biased toward threat detection. They are more likely to interpret ambiguous facial expressions as negative, more likely to remember social rejection, and less likely to trust others, all cognitive biases that further perpetuate isolation. It's a feedback loop. Loneliness breeds inflammation, which rewires the brain toward hypervigilance. which then deepens loneliness. There's also a profound impact on sleep, which serves as the body's repair mechanism. Individuals experiencing loneliness often exhibit more fragmented sleep, reduced slow-wave deep sleep, and increased nighttime awakenings. This impairs the glymphatic system's ability to clear metabolic waste from the brain, including beta amyloid and tau proteins, both associated with Alzheimer's disease. So in a very real sense, the experience of loneliness can accelerate biological aging and cognitive decline through inflammatory pathways. Interestingly, even brief improvements in social connection can begin to reverse some of these inflammatory markers. When people engage in meaningful social interaction, face-to-face conversation, physical touch, or community activity, the parasympathetic nervous system is activated, particularly the vagus nerve. This vagal tone helps regulate immune function and suppress the pro-inflammatory response. The brain interprets this as safety, downregulates the HPA axis, and allows neural repair processes to resume. From a systems neuroscience perspective, loneliness is not a soft or secondary concern. It is a full-body state that engages endocrine, immune, and neural systems in ways that directly impact health span and lifespan. The aging brain, already susceptible to structural and functional decline, is especially vulnerable to the effects of chronic social isolation. And because inflammation is a common denominator across nearly every major age-related disease, cardiovascular, neurodegenerative, metabolic, the link between loneliness and neuroinflammation has massive implications for public health and longevity. So the takeaway isn't just that loneliness feels bad, it's that loneliness ends chemically, structurally, immunologically. It is a biologically encoded alarm signal, and unless that signal is resolved through reconnection and social engagement, it continues to drive changes in the brain that quietly erode resilience and cognitive integrity. Reconnecting, even in small ways, isn't just psychologically uplifting, it's biologically protective. It's neural medicine. Cortisol is often referred to as the body's primary stress hormone, but that label doesn't capture its true complexity. In reality, cortisol is a finely tuned biological signal that follows a predictable diurnal rhythm, rising sharply within 30-45 minutes after waking, known as the cortisol awakening response CAR, then gradually declining throughout the day, reaching its lowest point late in the evening. This pattern is crucial. It helps regulate alertness, immune function, energy metabolism, and even the timing of other hormones. In a well-synced system, that rhythm is consistent, reliable, and adaptive. But when a person becomes socially isolated, especially over a sustained period, that rhythm begins to dysregulate. And the effects are not subtle. Isolation acts as a form of chronic, low-grade stress. The brain registers the lack of social interaction as a signal of danger, triggering the hypothalamic pituitary adrenal HPA axis to adjust cortisol output accordingly. This results in a disruption of the normal cortisol curve. In many cases, the cortisol awakening response becomes blunted. Instead of a sharp rise in the morning, there's a flattened trajectory, less energy, less drive, less cognitive sharpness. This blunting is strongly correlated with feelings of loneliness, fatigue, and cognitive fog. What makes this particularly important is that the CAR is not just about waking up. It plays a role in setting the tone for the rest of the day's brain and body function. A strong morning cortisol response helps facilitate attention, working memory, and emotional regulation by modulating activity in the prefrontal cortex and hippocampus. When that response is weakened due to isolation, those circuits operate at suboptimal levels. The result is often a sense of sluggishness, mental dullness, or low motivation, not because of willpower, but because the neurochemical signal that kickstarts the day is missing its peak. At the other end of the spectrum, isolation can also lead to elevated evening cortisol levels. In a healthy rhythm, cortisol should decline as the day progresses, allowing for relaxation, parasympathetic activation, and eventually sleep. But for individuals experiencing chronic isolation, the perception of threat remains persistent throughout the day and the HPA axis fails to shut down properly. Cortisol levels remain elevated into the evening, interfering with melatonin production and disrupting the onset of deep, restorative sleep. This can lead to more nighttime awakenings, lighter sleep stages, and a reduced ability for the brain to clear out metabolic waste via the glymphatic system. And here's where the pattern becomes even more concerning. Both the blunted morning peak and the elevated evening cortisol create a kind of biological noise. A signal-to-noise ratio of daily cortisol rhythms breaks down. The brain and body no longer receive the clear time-of-day information they need to coordinate physiological processes. Circadian rhythms begin to drift, mood regulation becomes more unstable. Appetite hormones like ghrelin and leptin get thrown off balance, increasing cravings for sugar and processed foods. Insulin sensitivity declines. The entire system starts to behave as if it's in a prolonged state of threat, even in the absence of any immediate danger. There's also a feedback mechanism at play. As cortisol patterns degrade, the brain's capacity to interpret social cues weakens. The amygdala becomes more sensitive to threat, the prefrontal cortex less able to inhibit reactive behavior. This makes social interactions feel riskier or more draining, further reinforcing the tendency to withdraw. In this way, the altered cortisol rhythm doesn't just result from isolation, it actively unsustains. Longitudinal studies show that individuals with flattened or erratic cortisol rhythms are at greater risk for depression, cardiovascular disease, cognitive impairment, and even early mortality. And in older adults, where the baseline capacity for stress regulation is already diminished, these disruptions can accelerate functional decline. But it's important to recognize that this process is not fixed. The HPA axis remains plastic. It responds to behavior, light exposure, movement, and most powerfully, social interaction. Rebuilding social connection, even in small, consistent doses, can help restore cortisol rhythm. Something as simple as a 10-minute walk with another person in the morning light or a structured routine of phone calls with close friends can begin to realign the neuroendocrine system. The presence of another person, particularly in a familiar or emotionally safe context, signals safety to the nervous system. That signal travels back up to the hypothalamus and, with repetition, begins to reshape the timing and amplitude of cortisol release. So when we talk about isolation, we're not just talking about being alone, we're talking about a biological shift in one of the body's core regulatory systems, a shift that affects cognition, sleep, immunity, and aging. And by understanding the mechanics of that shift, how cortisol patterns change in response to perceived social threat, we open the door to interventions that aren't just psychological, but deeply physiological. Reconnection, in this sense, is not just about emotional support. It's about restoring the rhythm of life itself.